Compressible flow. This topic introduces compressible flow, which is the basis for analyzing high-speed gas flows. In this type of flow, density variations can no longer be neglected, as in incompressible flow. This phenomenon is essential in applications such as aircraft, rockets, and gas turbines. Parameters such as pressure, temperature, and velocity are strongly coupled. This introduction forms the foundation for all subsequent discussions. Lesson Plan: Fluid Mechanics 2. The course structure shows that this chapter comes after Navier-Stokes and external flow. This sequence emphasizes that compressible flow is built upon previous fluid mechanics fundamentals. This chapter serves as a bridge toward turbomachinery and open-channel flow. Students are expected to be comfortable with momentum and energy concepts. This allows the focus to move directly to compressibility effects. Learning outcome. The learning outcomes emphasize understanding the physical consequences of gas compressibility. Students are also expected to understand why a nozzle requires a diverging section to reach supersonic speed. In addition, shock waves and property changes across them become a main focus. The effects of friction and heat transfer are also included in the analysis. Overall, the outcomes stress both conceptual understanding and analytical skills. Aircraft and jet engine real applications of compressible flow are shown through aircraft and jet engines. At high-speed conditions, kinetic energy cannot be neglected in the energy balance. Each jet engine component operates in a compressible flow regime. Significant pressure and temperature changes occur along the engine. This explains why compressible flow analysis is crucial in aerospace engineering. Steady flow in an adiabatic duct. Steady adiabatic flow means there is no heat transfer with the surroundings. Under this condition, the stagnation enthalpy remains constant along the duct. If the velocity increases, the static enthalpy must decrease. This shows the conversion of energy between kinetic and internal forms. This principle becomes the basis for many nozzle and diffuser analyses. Check your understanding. Number 1. In a control volume with steady, adiabatic fluid flow, the principle of energy conservation ensures that the total enthalpy remains constant across the duct. Fluid states on an HS diagram. The HS diagram is used to visualize changes in fluid states. The isentropic stagnation state represents the ideal condition, with no entropy increase. In real conditions, friction causes stagnation pressure to drop and entropy to rise. Kinetic energy is converted into enthalpy when the fluid is brought to rest. This diagram is very helpful for understanding the difference between ideal and real processes. Temperature rise during stagnation. When a gas flow is brought to rest, its kinetic energy is converted into internal energy. This conversion causes a temperature rise even without external heat input. The magnitude of the temperature increase depends on the initial flow velocity. A simple example shows that even 100 meters per second produces a measurable effect. This concept is important in stagnation temperature measurements. Variation of fluid properties in a duct. In compressible flow, a pressure drop is always accompanied by changes in other properties. Velocity and Mach number increase as pressure decreases. In contrast, density and temperature tend to decrease. The cross-sectional area also plays a role in controlling flow behavior. This graph shows the strong coupling among flow properties. Nozzle flow and throat. The throat is the minimum area section that controls the flow behavior in a nozzle. For subsonic flow, the converging section accelerates the flow. To reach supersonic speed, a diverging section is required after the throat. Pressure keeps decreasing while velocity keeps increasing in the diverging part. This concept is the key to rocket and gas turbine nozzle design. Check your understanding. Number 2. Which of the following best describes the function of a converging-diverging nozzle? B. Accelerates fluid to supersonic speeds after the throat, with the diverging section reducing pressure and increasing velocity further. Explanation of incorrect options. A. Reduces pressure in a subsonic flow and decelerates the fluid after the throat. This is incorrect because the converging-diverging nozzle accelerates the fluid to supersonic speeds after the throat. The fluid is not decelerated after the throat unless flow conditions are improperly managed, such as shocks. C. Maintains constant velocity while decreasing pressure across the entire nozzle. This is incorrect because the velocity does not remain constant. The nozzle's design ensures acceleration in both converging and diverging sections for subsonic and supersonic flows, respectively. D. Increases velocity in the converging section and maintains the same velocity in the diverging section. This is incorrect because the diverging section of a converging-diverging nozzle is designed to further accelerate the fluid to supersonic speeds, not maintain the same velocity. Energy equation for isentropic flow. The energy equation for isentropic flow is simplified by neglecting heat transfer, work, and potential energy. Under this condition, the sum of enthalpy and kinetic energy per unit mass remains constant. By differentiating the equation, the relationship between changes in pressure, velocity, and density can be obtained. Isentropic thermodynamic relations directly link pressure and enthalpy. This equation becomes the basis for analyzing ideal nozzle and diffuser flows. Converging nozzle limitations. Extending the converging section only shifts the sonic point downstream. However, this method never produces supersonic flow. In fact, the mass flow rate can even decrease due to changes in flow conditions. To achieve supersonic speed, a diverging section is mandatory. This shows the physical limitation of a purely converging nozzle. Flow properties in nozzles and diffusers for subsonic and supersonic flows is very different in nozzles and diffusers. For subsonic flow, a nozzle reduces pressure and increases velocity, while a diffuser does the opposite. For supersonic flow, the same trends occur, but with different physical mechanisms. The Mach number becomes the key parameter that determines the direction of property changes. This concept is essential in high-speed flow system design. Critical properties at nozzle throat. At the throat, the Mach number is always equal to 1. At this condition, temperature, pressure, and density reach their critical values. These critical properties apply to both subsonic and supersonic nozzles. The throat becomes the main control point of the entire flow behavior. Therefore, nozzle analysis almost always starts from this critical condition. Check your understanding. Number 3. The throat is the critical location in nozzle flow where the Mach number reaches 1, marking the transition point for analyzing the flow behavior in both subsonic and supersonic regimes. Critical ratios for isentropic flow of ideal gases. This table shows the critical ratios of pressure, temperature, and density for various ideal gases. These values depend on the specific heat ratio K. For air, the critical pressure ratio is about 0.528 of the stagnation pressure. Each type of gas has its own characteristic in reaching sonic conditions. This data is very important for practical nozzle and duct flow calculations. Critical ratios for isentropic flow of ideal gases. As the value of K increases, the critical pressure ratio tends to decrease. The same trend is observed for the critical temperature ratio. However, the density ratio does not change drastically among gases. This shows that thermodynamic properties strongly influence compressible flow behavior. Understanding this table helps in selecting the appropriate gas model in engineering analysis. The back pressure on converging nozzle. The back pressure determines the pressure distribution along the nozzle. If the back pressure is higher than the critical pressure, the flow remains subsonic. When the back pressure is reduced to or below the critical pressure, the flow becomes choked at the throat. Under this condition, the exit pressure cannot decrease any further. This phenomenon shows the existence of downstream control limits. Effect of back pressure on mass flow rate and exit pressure. The mass flow rate increases as the back pressure is reduced until it reaches a maximum value. After the choking condition is reached, the mass flow rate is no longer affected by the back pressure. The exit pressure follows the back pressure only before choking occurs. After choking, the exit pressure is locked at the critical value. This graph explains why flow systems have a maximum capacity limit. Mass flow rate variation with stagnation properties. When the flow is choked, the mass flow rate is no longer affected by downstream pressure. However, the mass flow rate is still strongly influenced by the stagnation pressure and temperature. Increasing the stagnation pressure or decreasing the stagnation temperature will increase the mass flow rate. Conversely, decreasing the stagnation pressure or increasing the stagnation temperature will reduce it. This shows the importance of upstream conditions in controlling flow capacity. Answer C. PB is less than or equal to P star. Explanation: A. PB is greater than P star. This is incorrect because if the back pressure is greater than the critical pressure, P star, the flow would not be choked and would be subsonic. B. PB equals P star. This is incorrect as it is the condition where the flow is at the threshold of becoming choked, but it doesn't state that the flow is maximized yet. C. PB is less than or equal to P star. This is the correct answer, as the flow becomes choked when the back pressure is less than or equal to the critical pressure, leading to a maximized mass flow rate that is independent of downstream conditions. D. PB is greater than P star. This is incorrect because this would imply the flow is not choked and would be subsonic, leading to lower mass flow rates. 4.0 Mini. Property ratios for isentropic flow. At Mach number equal to 1, all property ratios reach their critical values. As Mach increases from subsonic to supersonic, the pressure and density ratios continue to decrease. The change in area ratio is relatively small around sonic conditions. This shows that the region near Mach 1 is very sensitive to changes in flow conditions. This table is very useful for interpolation in practical calculations. This image shows a real example of a propulsion system based on compressible flow. The combustion chamber produces high temperature and high pressure gases. The nozzle then converts this thermal energy into kinetic energy. This process generates a very high-speed jet. The same principle is used in rocket engines and jet engines. Converging, diverging nozzles in rocket engines. In a rocket engine, the combustion chamber produces gases with very high pressure and temperature. The converging section accelerates the subsonic flow toward the throat. At the throat, the flow reaches sonic conditions, and the mass flow rate becomes maximum. The diverging section then accelerates the flow to supersonic speed to produce large thrust. This design allows very efficient conversion of thermal energy into kinetic energy. Effects of back pressure in converging diverging nozzle. If the back pressure is still high, the flow remains subsonic or only reaches sonic conditions at the throat. At intermediate back pressure, a shock wave can form inside the nozzle. This shock forces the flow to change from supersonic back to subsonic. If the back pressure is low enough, the flow remains supersonic all the way to the exit. This last condition produces maximum thrust. Flow across a normal shock wave. A normal shock wave causes a supersonic flow to suddenly become subsonic. Pressure, density, and temperature increase discontinuously. In contrast, velocity and Mach number drop sharply. This process is irreversible and is always accompanied by an increase in entropy. This phenomenon is very important in the design of engine inlets and nozzles. Check your understanding. 5. Across the shock wave, the flow transitions from supersonic, Mach 1 greater than 1, to subsonic, Mach 2 less than 1, with an increase in pressure, density, and temperature. Normal shock in a Laval nozzle. In a Laval nozzle, a normal shock can appear in the diverging section. Before the shock, the flow is usually at a Mach number around 1.3 or higher. The interaction between the shock wave and the boundary layer distorts the shock shape. This effect often triggers flow separation near the wall. This condition significantly reduces nozzle performance. HS diagram for flow across a normal shock. On the HS diagram, the process across a shock wave is shown as a movement along the shock curve. The total enthalpy remains constant, even though the static enthalpy increases. Entropy always increases because this process is irreversible. The Mach number change from greater than 1 to less than 1 is also clearly visible. This diagram helps visualize the thermodynamic consequences of shock waves. Flow properties across a normal shock. After passing through a normal shock, the static pressure and density increase significantly. At the same time, the stagnation pressure decreases due to irreversibility. The velocity and Mach number drop to subsonic values. The static temperature increases, but the stagnation temperature remains constant. This combination of changes shows that a shock wave is very detrimental from a useful energy standpoint. Air inlet design for supersonic jets. In supersonic aircraft, the air must be decelerated before entering the compressor. Shock waves are used to reduce the Mach number from supersonic to subsonic. This process also increases the air pressure and temperature. A good inlet design maximizes stagnation pressure recovery. This strongly determines the performance and efficiency of the jet engine. Answer: B. To decelerate supersonic air to subsonic velocities for efficient engine operation. Explanation: A. To increase engine fuel efficiency. This is incorrect because the shock wave's role is not directly related to fuel efficiency, but to air deceleration for optimal engine conditions. B. To decelerate supersonic air to subsonic velocities for efficient engine operation. This is the correct answer because the shock wave's primary function is to slow down supersonic air to subsonic speeds, allowing proper conditions for engine operation. C. To decrease air temperature and pressure before entering the engine. This is incorrect because the shock wave increases air pressure and temperature, not decreases it, to ensure efficient combustion in the engine. D. To stabilize engine combustion during high-speed flight. This is incorrect because while the shock wave helps with air deceleration, it doesn't directly stabilize combustion, which is more influenced by engine design and fuel-air mixing. This section serves as a transition toward discussing shock wave phenomena on a broader scale. The focus shifts from internal applications, such as nozzles and inlets, to free space phenomena. Visual examples will help in understanding the physical nature of shock waves. This approach makes it easier to connect theory with experimental observations. As a result, conceptual understanding becomes stronger. Expanding spherical shock wave from a firecracker explosion. An explosion generates a spherical shock wave that propagates in all directions. Initially, this wave travels at supersonic speed. As the distance increases, its intensity and speed decrease. The pressure rises sharply when the shock wave passes a point. Schlieren visualization clearly reveals the density changes.
Entropy change across a normal shock. A normal shock can only occur if the upstream flow is supersonic. After passing through the shock, entropy always increases. This increase in entropy indicates an irreversible process. A decrease in entropy across a normal shock is physically impossible. This principle is consistent with the second law of thermodynamics.
This part marks the transition toward discussing oblique shocks and external aerodynamic phenomena. The focus is no longer limited to one-dimensional flow. The interaction between body geometry and the flow becomes very important. Visualization plays a major role in understanding flow patterns. This prepares the discussion of oblique shocks and expansion fans. Supersonic wind tunnel testing of space shuttle conditions. At Mach 3, various oblique shock waves form around the model. The Schlieren technique allows visualization of air density changes. From these results, pressure and temperature distributions can be analyzed. Such data is very important for aerodynamic design optimization.
Oblique shock and flow deflection. An oblique shock forms when a supersonic flow encounters a wedge or a small angle surface. The flow is then deflected by a certain angle after passing the shock. The shock angle and the deflection angle are related to each other. After the shock, the Mach number decreases but can remain supersonic. This phenomenon is very common on wings and control surfaces of supersonic aircraft. An oblique shock forms at a shock angle beta due to a slender wedge with a half angle delta, resulting in a deflection of the flow downstream, altering its direction. Velocity vectors in oblique shocks. The upstream velocity can be decomposed into tangential and normal components relative to the shock. The normal component undergoes changes similar to those in a normal shock. The tangential component remains unchanged across the shock. After passing the shock, the direction of the velocity vector changes according to the deflection angle. This vector approach simplifies the mathematical analysis of oblique shocks. Velocity and Mach numbers in oblique shocks. By rotating the coordinate system, an oblique shock can be treated as a normal shock, acting on the normal component of the flow. The upstream normal Mach number is greater than 1, while the downstream normal Mach number becomes less than 1. However, the total downstream Mach number can remain greater than 1. Pressure always increases after the shock. The downstream flow direction follows the deflection angle. Relationships across an oblique shock. The downstream flow properties are determined by the upstream normal Mach number and the specific heat ratio. Pressure and temperature increase as the shock becomes stronger. Density also increases, while velocity decreases. These relations allow quantitative calculation of conditions before and after the shock. Therefore, oblique shocks can be analyzed in a systematic way. Answer C. Downstream pressure and temperature increase with upstream Mach number and shock strength. Explanation. A. Downstream Mach number increases while pressure and temperature decrease. This is incorrect because after an oblique shock, the Mach number actually decreases and pressure and temperature increase, not decrease. B. Downstream density decreases and velocity increases based on upstream flow conditions. This is incorrect as the downstream density increases and velocity decreases after the shock, which is the opposite of what is stated here. C. Downstream pressure and temperature increase with upstream Mach number and shock strength. This is the correct answer, as the pressure and temperature increase downstream due to the shock strength and the upstream Mach number. D. Downstream Mach number remains unchanged and the velocity remains constant. This is incorrect because the Mach number decreases after the shock and the velocity also decreases, not remaining constant.
This part serves as a transition toward discussing deflection limits and different types of oblique shocks. The focus shifts from a single configuration to a more general characteristic map. The concepts of weak and strong shocks will be introduced. In addition, the physical limits of oblique shock existence will be discussed. This transition is important for understanding the limitations of supersonic aerodynamic design.
Deflection angle and oblique shock characteristics. There is a maximum deflection angle that still allows an oblique shock to exist. To the left of this limit, only weak shocks occur, with relatively small pressure increases. To the right, strong shocks appear, and the downstream flow becomes subsonic. The sonic line marks the condition where the downstream flow is exactly at Mach 1. A higher upstream Mach number enlarges the range of possible deflection angles. Detached oblique shock characteristics. If the wedge angle is too large, the oblique shock can no longer remain attached to the body. In this case, the shock detaches and forms a bow shock in front of the body. Its shape becomes curved rather than straight. The flow properties become more complex in the region between the body and the shock. This phenomenon commonly occurs for blunt bodies in supersonic flow.
Schlieren visualizations of shock detachment. At small cone angles, the shock remains attached to the cone surface. When the angle is increased, the shock moves away and eventually detaches. Schlieren visualization shows this change very clearly. The transition from attached to detached shock indicates a clear geometric limit. This is very important in the design of rocket noses and space vehicles.
Flow characteristics around a sphere. In front of a sphere, a bow shock forms with subsonic flow behind it. The laminar boundary layer separates at a certain angle from the surface. After separation, the flow becomes turbulent and forms a wake behind the body. Disturbances in the wake can merge into a secondary recompression shock. This pattern shows how complex supersonic flow around blunt bodies can be. At an angle of 90 degrees, the laminar boundary layer separates, creating an oblique shock and transitioning to turbulence.
Expansion fan in supersonic flow. An expansion fan occurs when a supersonic flow is turned away from a wall or a corner. Unlike a shock wave, this process occurs gradually and is isentropic. As the flow passes through the expansion fan, pressure and temperature decrease. In contrast, the Mach number and velocity increase. This mechanism is very important in the design of supersonic ducts and surfaces. This part serves as a bridge toward more complex visual examples of supersonic flow. The focus shifts from ideal models to real phenomena around three-dimensional geometries. The visualizations will show combinations of shock and expansion waves. This approach helps connect theory with experimental observations. As a result, the understanding of flow patterns becomes more complete. Flow characteristics around cone, cylinder, and wedge. Around a cone-cylinder configuration, the boundary layer quickly becomes turbulent. Mach waves and expansion waves are clearly visible in Schlieren or shadowgraph images. Small angle geometries produce similar wave patterns for cones and wedges. The interaction between waves and the boundary layer affects the pressure distribution. This example shows the complexity of real supersonic flows.
Shock and expansion wave interactions in overexpanded jets. In an overexpanded jet, the exit pressure is lower than the ambient pressure. This condition causes a series of alternating shock and expansion waves to form. This pattern is often called a tiger tail in color-Schlieren visualizations. The flow structure becomes highly non-uniform and periodic. This phenomenon is commonly observed in rocket and jet engine nozzles.
Answer: C. Tiger tail pattern. Explanation: A. Supersonic jet dynamics. This is incorrect because while the jet dynamics involve complex flow phenomena, it does not directly refer to the alternating pattern of shocks and expansions seen in the Schlieren imagery. B. Schlieren visualization. This is incorrect because Schlieren is a technique used for flow visualization, but the question asks about the specific pattern in the imagery, not the technique itself. C. Tiger tail pattern. This is the correct answer, as it describes the distinct alternating pattern of shocks and expansions that resemble a tiger tail, seen in color-Schlieren imagery. D. Turbulent wake. This is incorrect, because the turbulent wake refers to the flow downstream of the jet, which is not the primary focus of the alternating shock and expansion pattern described in the question. Weak and strong oblique shock solutions. For the same wedge angle, two types of oblique shock solutions can exist. A weak shock produces a smaller pressure rise and keeps the downstream flow supersonic. A strong shock produces a large pressure rise and makes the downstream flow subsonic. In practice, the flow almost always selects the weak shock solution. This understanding is important in supersonic aerodynamic design. Expansion fan from sudden wall expansion. When a wall suddenly expands, a supersonic flow forms an expansion fan. The flow is accelerated and turned smoothly without any discontinuity. Pressure and temperature decrease during this process. There is no entropy increase because the process is isentropic. This is the physical opposite of a shock wave. Combustion in compressible flow strongly affects compressible flow properties. Pressure, temperature, and velocity can change significantly along the duct. Such systems are commonly found in jet engines and ramjets. The mixing of fuel and air must be carefully controlled. Compressible flow models with combustion are essential for engine performance analysis. Flow in constant area duct. Changes in flow properties are mainly caused by heat transfer. Friction is often neglected to focus the analysis on heat effects. The energy balance is used to relate inlet and exit conditions. Even though the area is constant, pressure, temperature, and velocity can still change. This model forms the basis of Rayleigh flow analysis. In analyzing flow behavior with external heat, the energy balance examines energy transfer within the control volume to understand the effects of heat transfer. Rayleigh flow analysis. In Rayleigh flow, the main effect considered is heat addition or removal. For subsonic flow, heating accelerates the flow toward sonic conditions. For supersonic flow, cooling decelerates the flow toward sonic conditions. The maximum temperature is reached when the flow becomes sonic. This condition represents the critical point in Rayleigh flow analysis. Effect of heating on Rayleigh flow. For subsonic flow, heating can either increase or decrease the static temperature depending on the initial Mach number. However, the stagnation temperature always increases when heat is added. For supersonic flow, heating always increases both static and stagnation temperatures. This shows that the flow response depends on the speed regime. The Mach number becomes the key parameter in determining the direction of change. This part serves as a bridge toward a quantitative summary of heating and cooling effects. The focus expands from qualitative concepts to trends in various property changes. Diagrams and tables help clarify the relationships among variables. This approach is important for engineering calculation applications. As a result, the understanding becomes more systematic. Effects of heating and cooling on Rayleigh flow. Heating and cooling affect velocity, Mach number, temperature,
pressure, density, entropy in different ways. For subsonic flow, heating tends to increase the Mach number and velocity. For supersonic flow, heating instead reduces the Mach number and velocity. Pressure always decreases with heating for both subsonic and supersonic flows. Entropy always increases when heat is added. Impact of heating on flow velocity. In subsonic flow, adding heat accelerates the flow. In supersonic flow, adding heat instead decelerates the flow. This opposite behavior is a characteristic feature of Rayleigh flow. This can be explained through changes in density and internal energy. This understanding is important in the design of combustors and afterburners. Answer B. Heating increases velocity in subsonic flow, but decreases it in supersonic flow. Explanation. A. Heating increases velocity in both subsonic and supersonic flows. This is incorrect because heating causes an increase in velocity in subsonic flow, but leads to a decrease in velocity in supersonic flow. B. Heating increases velocity in subsonic flow, but decreases it in supersonic flow. This is the correct answer because heating accelerates subsonic flow due to energy addition, while in supersonic flow, heating absorbs energy, causing deceleration. C. Heating decreases velocity in both subsonic and supersonic flows. This is incorrect because heating only decreases velocity in supersonic flow, not in subsonic flow. D. Heating decreases velocity in subsonic flow, but increases it in supersonic flow. This is incorrect because the opposite trends occur. Heating increases velocity in subsonic flow and decreases it in supersonic flow. Summary of Rayleigh flow relations. Rayleigh flow relations connect changes in temperature, pressure, density, and velocity with the Mach number. These equations allow calculation of flow conditions before and after heat addition. The stagnation temperature always changes according to the amount of heat added. The stagnation pressure, on the other hand, decreases due to irreversibility. This summary is very helpful in the analysis of combustion systems. Maximum heat transfer in Rayleigh flow. There is a maximum amount of heat that can be added to the flow. This limit is reached when the flow becomes sonic at the duct exit. At this condition, the flow is said to be choked by heating. Further heat addition is not possible without changing the inlet conditions. This concept is very important in combustor design.
Adiabatic flow in constant area ducts. In Fanno flow, the main effect considered is wall friction. Even though there is no heat transfer, friction still changes the flow properties. Pressure decreases and entropy increases along the duct. The total energy remains constant because the flow is adiabatic. This model is very important for analyzing flow in long pipes. TS diagram for Fanno flow. The TS diagram shows that maximum entropy is reached when the flow becomes sonic. For subsonic flow, friction accelerates the flow toward Mach 1. For supersonic flow, friction instead decelerates the flow toward Mach 1. Temperature decreases in subsonic flow and increases in supersonic flow due to friction. This diagram provides a very clear visual picture of Fanno flow behavior. In supersonic flow, friction increases temperature, while in subsonic flow, friction reduces it. Frictional effects in Fanno flow. In subsonic flow, friction increases the Mach number and reduces the temperature. In supersonic flow, friction decreases the Mach number and increases the temperature. Both types of flow move toward sonic conditions. This shows that friction always drives the system toward the critical state. This behavior is a characteristic of Fanno flow. Adiabatic flow with friction. Differential analysis is used to examine small changes in flow properties along the duct. Friction causes pressure loss and changes in density and velocity. The cross-sectional area remains constant, so the changes are purely due to friction. Although the total energy remains constant, its distribution between internal and kinetic forms changes. This model is important for understanding real flows in pipes. This part serves as a bridge toward a quantitative summary of friction effects. The focus shifts to a summary of changes in various flow properties. This approach helps unify conceptual and numerical understanding. Tables and summarized relations become the main tools. As a result, the overall picture of Fanno flow becomes clearer. Effects of friction in Fanno flow. In subsonic flow, friction increases velocity and Mach number. In supersonic flow, friction decreases velocity and Mach number. Static temperature decreases in subsonic flow and increases in supersonic flow. Density decreases in subsonic flow and increases in supersonic flow. Entropy always increases in both flow regimes. Answer B. Friction increases the Mach number in subsonic flow and decreases it in supersonic flow. Explanation. A. Friction decreases the Mach number in subsonic flow and increases it in supersonic flow. This is incorrect because friction decreases the Mach number in subsonic flow and increases it in supersonic flow, opposite to what's stated here. B. Friction increases the Mach number in subsonic flow and decreases it in supersonic flow. This is the correct answer. Friction accelerates subsonic flow, increasing the Mach number, and decelerates supersonic flow, decreasing the Mach number. C. Friction increases velocity in subsonic flow and decreases velocity in supersonic flow. This is incorrect because friction causes velocity to increase in subsonic flow but causes a decrease in supersonic flow, which matches the velocity trend but not the statement. D. Stagnation temperature increases in both subsonic and supersonic flow due to friction. This is incorrect because the stagnation temperature remains constant regardless of the flow being subsonic or supersonic, even with friction. Compressible flow. The sonic condition is used as an important reference state in compressible flow analysis. From any point in the duct, there is a characteristic length to the sonic condition. All properties, such as pressure, temperature, and velocity, evolve toward this state. This shows that the Mach 1 condition is an important physical limit. This concept unifies the analysis of Rayleigh and Fanno flows. Summary of Fanno flow relations. Connect changes in pressure, temperature, density, and Mach number with friction. All these relations are expressed relative to the sonic condition. With these relations, the maximum duct length can be calculated. The stagnation pressure always decreases due to friction. This summary is very important for gas pipe and duct design applications. Behavior of supersonic Fanno flow. If the duct is long enough, a supersonic flow will reach sonic conditions at the exit. If the duct is extended further, a normal shock will be pushed upstream. After passing the shock, the flow becomes subsonic. The combination of friction and shock produces a complex property distribution. This phenomenon is important in the design of high-speed piping systems. In supersonic Fanno flow, the flow becomes sonic at the duct exit when the length exceeds a critical value. References. The main reference for this chapter comes from the textbook by Chengel and Jimbala on fluid mechanics. All figures and main concepts are taken from this source. This book is one of the standard references in fluid mechanics education. Mastering this chapter means mastering the fundamentals of engineering compressible flow. This reference also serves as a foundation for advanced studies in aerodynamics and turbomachinery.